It's my pleasure to welcome the second speaker of the day, Karima Khusnutdinova from Loughborough University, and she will talk about undular bores generated by fracture.
Thank you very much, Thibaut, and thank you very much to all organizers for organizing this excellent event. I will try to tell you about our very recent work, and certainly we are here making mainly the first steps, and a lot more is to do, but I hope to tell you about some difficulties that we are facing here, and about some things that we managed to understand at the moment. So this work began a few years ago when Pablo Ruiz, a colleague from the engineering department in Loughborough, whom I did not know at the time, knocked at my door, at the door of my office, and asked to help to understand the nature of some signals which he registered following tensile fracture. So these were some measurements of optical intensity. They did not look, they looked nothing like undular bores at the time, and it took us quite a while to, and quite a lot of work both on the experimental and theoretical fronts in order to make some sense of these signals, and that's what I will try to tell you about. So this work was done, most of it was done by our PhD student, Curtis Hooper, and colleagues from engineering department, Pablo Ruiz and Jonathan Huntley. They helped him with the experimental part of the work, and I helped to with the theoretical part, and also guiding what could be changed in experiments, what could be, how could we modify the experiments, and so on. Okay, so as I expected, the previous talk already introduced the listeners to the subject of undular bores, and so I decided to skip the introduction, and I will start by showing you some experimental measurements. Then I will discuss the model equation. So in this area, we are pretty much at the level where we are trying to establish a good model which is capable of describing the phenomena. Parameter fitting, which turned out to be a rather challenging problem in its own right. Some numerical simulations, linear bore approximation, and I will try to make some conclusions. So this work was funded mainly by the Wolfson School of Mechanical, Electrical and Manufacturing Engineering at Loughborough University, with some additional contribution from the School of Science, and we're very grateful for that funding. Okay, so these are the experimental results from two different series of experiments. The first, the measurements on the left are from the natural fracture experiments. I will show you the experimental setup in a minute. And the measurements on the right are from the induced fracture experiments. So this was a second series, which, by the way, unfortunately was very significantly delayed by the restrictions related to COVID-19. For a long time, no experiments were possible. Everything was in lockdown here and so on. So this work was done in pretty difficult conditions, I must say. Okay, so I will return to this in a second. So this is the schematic of the experimental setup. So we have a bar with the dimensions of cross-section is rectangular cross-section 3 millimeters by 10 millimeters, and the length of this bar was 75 centimeters. Okay, so it was made of the material called polymethylmethacrylate, or PMMA, and we all know it as plexiglass. Okay, so this specimen, this sample, was put in a tensile machine, and so this picture was actually vertical, right? So here it's presented in horizontal configuration, but in a lab it is in a vertical tensile machine, and it has been loaded, okay, until tensile fracture. There was a place where the sample was pre-notched so that fracture was happening, obviously, in this place, okay? And then optical techniques were used in order to register the deformation in the sample. So, of course, what was registered was optical intensity, but this was then used to reconstruct the strain. And this was measured every 5 centimeters from fracture site. Okay, so first measurement at 5 centimeters, then 10, and so on up to 50 centimeters. So photoelasticity was the method which was used here. And these are the measurements from this series of experiments. So we must understand that in this series of experiments, each curve is an individual experiment. Okay, so they were not measured in a single experiment. They were measured in different experiments where the optical setup was moved along the bar. And but conditions at fracture were similar. Nevertheless, there was, of course, some variation. And we see the emergence of this signal at the front, which is an undular bore. Of course, waves in solids are very complicated, and alongside longitudinal waves, there are also shear waves. And the region where we have shear waves is shown as this shaded region here. Okay, shear waves are moving slower. And so in this region, we have longitudinal waves, but here we have a mixture of both, and the technique doesn't allow us to separate. So in this second series of experiments, we managed to create a steeper slope. And this was done by pressing a blade against the sample at a certain pre-strain. And this technique allowed us, so as we anticipated, if we do that, we will see a much better developed undular bore and at an earlier distance. So this measurement is at 50 centimeters, this is at 30 centimeters, and we have this very recognizable signal looking as an undular bore. Okay, so when we started digging into all that, obviously we've read a lot of relevant papers, and we found that similarly looking strain waves have been reported in various impact tests. So there are so-called split Hopkinson pressure bar experiments in engineering. And there were other impact tests, and there were some very important papers by Kolsky and his team in the 60s on waves in steel. And Kolsky used the word chorda for what we would call undular bore. But from that time, as far as I have seen, the term has also been used to denote any dispersive radiation and not just undular bore. So therefore, it's kind of not an equivalent term to undular bore. So most of the time in this solid mechanics area, people, when they have something like, with oscillations, they just say dispersion. And that's more or less the description that is used. So there are very recent experiments on waves in steel in the papers by Wren and Sever and Jordan. And similar strain waves were also registered in impact tests with PMMA waveguide. But to the best of our knowledge, this is the first time when undular bores have been generated by tensile fracture. So we the strain of fracture was rather big, 1 to 2%. And so nonlinear corrections become important at that strain. And also we accounted for viscoelastic corrections to the leading order. So from what we have seen in the literature, in solid mechanics, people mainly studied waves. So firstly, they were studied in the linear context, and steel is pretty much linearly elastic material. So waves were studied using Fourier method, so Fourier harmonics, and various numerical techniques. Unlike fluid mechanics, where KdV type models, which can be viewed as an extension of D'Alembert's ideas, I think, have not been used. So neither nonlinear nor linearized models, and therefore these analytical descriptions that we have available in connection with fluid mechanics, they have not been used there, to the best of my knowledge. So I should also mention these papers. From the titles of these papers, it's clear that Kolsky and his team, they have registered waves generated by tensile fracture. In the context of our work, these are similar to measurements at the first distance. So essentially similar to our initial conditions, right? So in our work, we were interested in the subsequent evolution of these waves. And yeah, so from our perspective, these waves are similar to measurements close to the fracture site. Okay, so let me now start discussing the model equation. And here, instead of talking about rods, I would rather tell you a little bit about bars. I would like to tell you about rods with circular cross sections. So waveguides with a different cross section. So in this setting, theory can be done much cleaner. And I think this, our recent work with Garbuzov and Beltyukov, which builds on the whole body of previous research on longitudinal bulk strain waves in solids, which are listed here. Unfortunately, I don't have time to discuss this in detail. I will have to skip it. So this continued the research in the previous papers, and that's a rather systematic derivation, asymptotic derivation of an extended Korteweg de Vries equation. Let me just very briefly tell you about it. So this is done in Lagrangian coordinates. UVW are the axial, radial displacements and torsion. Derivations are done within the context of Landau energy of deformation, which is equivalent to Monaghan's non-constant model for the elastic energy. They're really equivalent, just use different invariants of the Cauchy-Green strain tensor. So derivation is computer assisted. Equations are very, very long because these right-hand sides are given by this expression. Yeah, that's the so-called Piola-Kirchhoff stress tensor. And you can imagine that with this kind of expression, where the C is this tensor, you are getting really, really long expressions. But nowadays, using Mathematica, using symbolic computations, it is possible to do systematic asymptotic derivations for this, for the problems of that complexity. So first of all, once the equations are formulated and the boundary conditions are formulated, so lateral surface is free from stress, we can check symbolically, so in the code, that the equations have an exact reduction to this problem where torsion is equal to 0 and nothing depends on phi, on the polar angle, okay? And all the problem is first of all reduced. And after that, we develop expansions, asymptotic expansions. in terms of the radial coordinate, non-dimensionalize the variables, and we see the emergence of two small parameters, amplitude and long wavelength parameter. Pretty much from that point, it's standard asymptotic analysis, derivations, and we can recover the famous Lough's hypothesis. So this ratio is the so-called Poisson's ratio. So Lough's hypothesis would be just the first two terms. This procedure gives all the high order corrections to this Lough's hypothesis, and it's no longer a hypothesis, right? It just follows from the derivation. And then assuming the balance between nonlinear and dispersive terms, an extended Boussinesque type equation can be derived in this form, okay? It's a systematic asymptotic derivation similar to how we do it in fluids, but it is technically much more complicated. And so next, the characteristic and slope variables are introduced, and we look for the model, unidirectional model, and we can derive this equation, which many of us know very well from the context of fluids, so-called extended Korteweg de Vries equation. Okay, so for the rod, this has been derived in a systematic fashion. So to justify applicability of this model, we have compared solitary wave solutions of the model with the exact numerical simulations of the original fully nonlinear problem formulation. Okay, so these were coded by my colleagues in the EOF Institute. And to initiate the runs, we used solutions which were obtained with the help of the near identity transformations. So these are results due to Kodama, Focus, and Liu. So there exist near identity transformations which map which map the extended KdV type equation to itself with just new parameters, right? So we found a particular transformation which maps an extended KdV equation to the Gardner equation. That's first of all. Gardner equation has a famous, well-known family of solitons. We've written it in the form which appeared, was used in the papers by Grimshaw, Pelinovsky, Telipova, and this team. And so when we applied the inverse near identity transformation in order to reconstruct the solution of the extended KdV equation, we obtained this, okay? So this was obtained using the direct transformation to Gardner and then inverse near identity transformation back to the extended KdV equation. And these are comparisons of the approximate solutions. So we initiate runs of the full equations of motion, which are shown in blue with this solution, and then compare both with the KdV. KdV is green, and red is our extended KdV, okay? So Gardner has two branches, so this is Gardner plus, and perhaps more instructive to look at Gardner minus, and we can see that for small amplitude, perfect agreement. As we start increasing the amplitude, agreement with KdV becomes worse and worse, but agreement with the extended KdV solution remains pretty good, all the way up to almost the tabletop soliton. Here agreement is, that's the limiting case for Gardner minus. Here agreement is not so good, but still the analytical solution allowed to very quickly generate the numerical tabletop soliton. So it can be used at least as a very good initial guess. And pretty good comparison all the way up to here, okay? So, right, for the bar, we don't have such a clean derivation. KdV has been obtained at the physical degree of rigor in this paper, and Gardner equation has been obtained using similar assumptions in that paper. And what we also did, we added, we counted for viscoelasticity within the scope of the model which was used by the Chinese team Lily Wong and his co-workers for the PMMA in impact tests. Okay, so it was suggested by this team that this model is good for PMMA, and we used it. I will have to skip the details because I start running out of time. So essentially, if we do that, at the times relevant to our experiment, we can show that the leading order effect of viscoelasticity at the level of unidirectional models is given by the term which is similar to Rayleigh dissipation, which we know from fluids. Okay, so overall, the model which we used is that it's extended Korteweg de Vries equation with this contribution from the viscoelasticity. Okay, so as you can see, at least within the scope of this framework, it's not the veKdV model. Viscoelastic term is rather proportional to E minus E naught is the value of the pre-strain when the fracture happens. Okay, so parameter fitting is an interesting story in its own right, because you have seen that to describe the complicated properties of a solid, you need quite a lot of parameters, right? And they are here. And then also the viscoelastic properties, and they are not known, right? So they must be taken from somewhere. And so instead of fitting the parameters of the energy, for example, we were decided to fit parameters of the equation. And for that, we used the first two measurements, 5 and 10 centimeters, where we first assumed that dispersive and high-order nonlinear corrections are not so essential, and we can use this hyperbolic equation method of characteristics. But the difficulty here is, of course, that there are experimental errors, and also each measurement is an individual experiment. They are not all from the single experiment. And so we needed to invent some kind of optimization procedure, right, which would allow us to come up with some values capable of describing all that despite all those errors. So, what we did was the following. So in the ideal world, taking 3 points on the slope and mapping them correctly to the next curve, we would be able to find the parameters of this equation, right? So, but that's in an ideal world. So therefore, what we did after that, we split the slope into more and more points. And then for each number of points, we were taking triples of points, finding the coefficients, and then averaging, okay? And that's what we have, right? So for the 3 values of parameters which we were fitting, by increasing the number of points, so we split a particular subinterval of the slope into more and more points, we found that there is a minimum, right? For both experiments with natural fracture and induced fracture, all these parameters had a minimum, a very flat minimum in that case, more sharper minimum in that case. And so this minimum produced good values of parameters which were good at describing our experimental curves, not just at first 2 distances, but at all subsequent distances, okay? Parameters, the main parameters were fitted only at the first 2 distances, but they worked for later distances as well. And that's the optimization procedure that we used. So to fit the viscoelasticity parameter, we used another limiting regime. So far away from the release waves, we neglect all oscillations, right? So, and the governing equation reduces to that, which can be solved. And then by comparing the post-strain regions at 2 distances, we fitted the value of the parameter nu. So these are the main coefficients. Finally, to fine-tune the solution, the 5th dispersion coefficient was fitted just at the front of the bore, such that the duration of the leading oscillation of the model matched the experiment exactly at the last recorded distance. And this automatically gave the extension of the bore without any additional fitting. Nonlinear coefficient A2 was fitted to match exactly the amplitude of the first oscillation, and this automatically improved the amplitude of the second oscillation. The intensity-dependent dispersive correction was not fitted at this stage, so the fitting of these high-order corrections, I guess, can be optimized, but that's where we are at the moment. And that's the comparison of our theoretical modeling results with the experimental results. Experimental results are in pink, theoretical results are in blue. I'm only showing them for the induced fracture experiment. And notice the difference. So this was fitted using just the ERF initial condition, right? The last measurement, this was fitted using the spline approximation for the actual measured experimental curve. And here you can see the improvement in the description of the first two oscillations, right? So the second oscillation goes down compared to the first oscillation. Also notice interesting feature. What we noticed was that the linearized Gardner model, linearized near the level of the pre-strain, gave a rather reasonable description of the release wave and the leading oscillation. Okay, it did not give the subsequent oscillations, but rather good at describing the first oscillation. And therefore, this solution for the linearized Gardner problem, which was obtained by just mapping the problem to the problem considered by Berry in connection with Undular bores in Ruiz. So this solution is rather informative and allows us to obtain quite a lot of features which can guide experiments and suggest what we can do in order to change the behavior of the bore. So these are some properties of the solution, and I probably just will emphasize that, you know, very sensitive to the slope, right, of the initial condition, and therefore clearly we will now try to make the slope even more steeper and to see an even better developed Undular bore. Also, the duration of the leading oscillation is actually independent on that, which is also an interesting feature. And actually, it was already checked in the subsequent experiments, which will be reported shortly. I'm very much aware that the time is running up, so let me just very quickly summarize. So generation of longitudinal Undular bores has been registered experimentally following natural and induced tensile fracture in PMMA bars. The viscoelastic extended KDV equation with appropriately fitted parameters is a good model for the distances relevant to the experiments up to 30 or 50 centimeters. A linear bore solution of the linearized Gardner equation was found to be rather useful, and I think we need to look more closely and to compare the behavior of the non-linear solutions which are obtained using the Witham averaging, because it seems that non-linear solutions and linear solutions might have perhaps some shared properties, right? And maybe we should have a look at hierarchies of models. This could be instructive, I think. Theoretical estimates from the solution are in agreement with experiments on bars of different widths to be reported soon. And we think that this is rather important because fracture is a process which is present both in nature and in the man-made world. It's something that is happening all the time, and there is nothing special that we are doing to generate the bores here, right? And we think that this could be present in the signals generated by earthquakes, fracking, and other similar events involving transverse fracture of an appropriately pre-strained waveguide. Thank you very much. I will stop here.
Thank you very much, Karima, for a very interesting talk. So do we have any questions? So do not hesitate to either write in the chat or raise your hand. So actually, I mean, I have a small question, Karima. So can you show again the slide with the linear bore, please? With the area.
Sorry, say it again.
Yeah, the one with the area function.
Solution, okay, yeah.
Because in this approximation, you would, okay, because would you expect that the amplitude of the area function will decrease with x or not in your approximation?
So first of all, I would like to emphasize one thing which I didn't, right? So notice that this solution is obtained with that initial condition with there, right? So that's not the integral area solution that we know.
Okay.
Yeah, so here you have the slope, the additional parameter. That's very important for when you try to compare something to experimental measurements, because you should be able to fit to the curves, experimental curves, which have different slope. So yeah. I don't know whether this solution has appeared before. We personally learned it from Barry's paper, okay? And it's pretty easy to map this problem to the problem which was considered in that paper, and that's how we did it. And that's the exact analytical solution of this problem. And by the way, it's also, I think it's a very useful solution. I mentioned at the start bores in steel, right, which were observed by a number of researchers. And steel is with a very good degree of accuracy, I think. You could think of it as being a linearly elastic material. And then this description where E tilde is E minus kappa, where kappa is the pre-strain level. So this will then be a solution which can be used in these experiments with impact tests. So for PMMA, that's an approximation, but for experiments in some other materials, which can be approximated as linear elastic, this should be, you know, almost exact. Should give very good description. Solids are very complicated media, and they have very, very different properties. On one hand, that's a complication that's difficult, but on the other hand, it's a completely new area of research where I think there are very, very many interesting problems, interesting and important problems. And we only scratch the surface of all that at the moment.
Yeah, I mean, because it looks very rich from the, from the point of view of dispersive hydrodynamics. I mean, it's.
Yeah, but I think, yeah, I hope, at least I hope that we all can agree that these signals are very similar to what we see in Ruiz, right? And
yeah.
Okay, thank you.
Thank you, Karima. So let me check if there is any end or no. So I think we can now have a break. So